So we're going to make an assumption throughout that the second moment exists, okay? And the reason is because we want to talk about variances and covariances, and so this is what you need to do. Don't think about it. This just means that everything I write will not be infinite at any point. Okay, so the first moment of a vector, so I can think of the moments of a vector, right? The moments of a random variable are expectation of x to the 1, expectation of x to the 2, expectation of x to the 3. When I have a vector, I have to be a little more careful. I have to know what it means to talk about a vector to the 2, vector to the 3, etc. So it turns out that there's a nice, compact mathematical way to think about it. It's called tensor product. But we'll only talk about the first two, and in the first two, it's even simpler. Okay, so the expectation of a random vector, you all know what it is. It's just the expectation of each of the coordinates, right? So it's a vector, and each of the coordinates is an expectation. So this is just the column vector. So I'm going to write it with the transpose up here. And so it's a column vector, and each of the coordinates is e of x1 all the way to e of xd. Okay, so I hope nobody's shocked by this. This is what the definition is of the expectation of a vector. And now if I want to talk about the second moment of a vector, if I want to talk about the variance of a vector, I actually have to form what's called the covariance matrix. And the covariance matrix captures not only the variance of each of the coordinates, but also the covariance between the coordinates of this vector. Okay, so I'm going to collapse them in this matrix. Capital sigma, it's of size d by d. So each row corresponds to one of the coordinates of xi. Each column corresponds to one of the coordinates of xi. And if I look at, for example, row jk, so row j, column k, then the entry that I have in this matrix is? Can somebody tell me what the sigma jk is in the covariance matrix? Correct? So it's the covariance of the jth coordinate and the kth coordinate. Okay, so that's the definition of my covariance matrix. Now, if I'm going to go to vectors, so here I have a vector and I form from it a matrix, which is my covariance matrix. But the way I describe this matrix is kind of useless because I describe it coordinate by coordinate. It would be nice if I could actually just tell you as a vector what it is. And so there's a matrix form for the covariance matrix, which is the following. So let's see what it is. So I claim that if I look at sigma, which is the expectation of x transpose minus the expectation of x times the expectation of x transpose, then if I look at the jkth coordinate, so sigma jk, then this will actually be the covariance between xj and xk. Okay, the way I've defined it from the coordinates is actually the same by doing this. Okay, so let's see what's on the jk entry. So when I look at xx transpose, what I'm really doing, so if I write xx transpose, this is a matrix that looks like, well, I look at x multiplied by x transpose, this vector. So the entry here in jk is what? What is the jk entry of the matrix xx transpose? Right, so how do I form the product between a vector and a column vector? Yes? Exactly, right? So this is xj, which was the number that we had here, and xk, which was the number that we had here. Okay, just take the product of those two, and that gives you this matrix. Okay, so if I look at the jkth entry of this matrix, what I have is xj times xk. Okay, so clearly, if I look at expectation of x transpose, and I view this as a matrix, and I look at the jkth entry of this guy, then this is just the expectation of xj times xk. Right? That's just saying the jkth entry of the expectation. So I first took the expectation. Well, I took the expectation afterwards here. Okay? But it's the same thing. So now, same thing if I look at expectation of x transpose, and I look at the jkth entry of this guy, well, what I started is not XX transpose, it's expectation of X transpose. So this product is expectation of Xj times expectation of Xk. So this thing is just expectation of Xj times expectation of Xk. And so when I subtract this guy from this guy, I really get exactly covariance of Xj and Xk. So that's telling me exactly this. Okay? So that's just a compact way of writing my covariance matrix, which will be useful.